Hello friends, in this video we are going to discuss about the third numerical related to the boost converter. So let us read the numerical. The input voltage to the following DC to DC converter is 20 volt. Okay, so it is given that the input voltage, that is a VDC, is equal to 20 volt. Okay, so VDC is equal to 20 volt. It is given. Next, the output voltage is 50 volt. V0 average is equal to 50 volt. That is a 50 volt. Next, the duty cycle D is equal to zero point 0.5. D is equal to 0.5. Okay. Our task is to find the RMS value of diode current. Okay. Let us consider it as a ID. ID RMS we need to find. Okay. So ID means which current? Yes, this diode current is nothing but the ID. Okay. We need to find the RMS value of this current. RMS value of this current. Okay. So now, first of all, let us check whether from the A circuit diagram we can say that it is a boost converter, right? But if you check, the duty ratio is 0.5, input voltage is 20 volt and the output voltage is 50 volt. Okay, so from this if you check, yes, for continuous conduction, yes, for continuous conduction, yes, what is the V0 or V0 average is equal to 1 upon 1 minus D, right, into VDC. Okay, but if you check, if we use this D, so it is like 1 upon 1 minus 0.5 into what is the VDC? VDC is 20, so it will be equal to 40 volt. Okay, but it is given that V0 average is equal to 50 volt. Okay, so here can we say that this V0 average for continuous conduction, yes, with a duty cycle of 0.5, yes, it is not equal to 50 volt. Okay, so can we say that, yes, therefore the conduction, yes, therefore the conduction should be discontinuous. Conduction should be discontinuous. Are you getting the point? Conduction should be discontinuous. Okay, now for the discontinuous conduction, yes, we are having expression for the V0 average. Yes, for discontinuous conduction, if you check the V0 average, we have already derived it in the last video, right? V0 average is equal to what? Beta upon beta minus D duty cycle into VDC. Okay, it is given that V0 average is 50 volt is equal to beta, we need to find, divided by beta minus D. D is 0.5. Okay, into 20. Okay, so from this if we check beta, yes, this beta, yes, it will be equal to 0.833 actually. Okay, so it is a 50 beta, yes, it is a 0.833, right? 0.833. Okay, or we can simplify it as a 50 beta minus 25, okay, is equal to 20 beta. Okay, so it is a 25 by 30 is nothing but the beta, so it is a 0.8333. Okay, so this is the beta, right, means the instant till which the inductor releases the energy, right? Inductor releases the energy. Also we are having, yes, the expression for IL average. Yes, also for discontinuous conduction, IL average, yes, we are having IL average is equal to what? Beta upon beta minus D into what? I0 or I0 average. Okay, so if you check, it is 0.833 divided by 0.833 minus zero point 0.5. Okay, into, yes, into it is a I0 average. Yes, what is the I0 average? I0 average is equal to, yes, we can find it as a V0 average divided by resistance 50. Okay, so it is a 50 by 50, right? Are you getting the point? I'm writing it as a V0 average divided by load resistance RL. Okay, so from this we can write it is equal to, yes, is equal to 0.833 divided by 0.833, right, minus zero point 0.5 into, yes, 50 upon 50. Okay, the resistance is also 50. Okay, and I have average output voltage also 50. Okay, So from this we can write it as equal to, therefore, yes, IL average, it is equal to 0.8333 divided by 0.8333 minus 0.5, so it is a 0.333. Okay, so it is equal to 2.5, equal to 2.5 ampere. Okay, so this is what IL average. Okay, why I have calculated the IL average is because if you check, when switch is in the on state, at that time the diode current will be 0, but when switch is in the off state, at that time, yes, IL is equal to ID. Okay, so can we draw the waveform for the ID? Yes, we can draw the waveform for the ID as, yes, waveform for the ID. Okay, so when switch is in the on state, right, it is time t 0, this is dt, this is beta t, and this is t. Okay, so when switch is in the on state, at that time ID is 0, right, but whereas when the switch is in the off state, at that time ID is equal to 2.5, right, so this magnitude will be equal to 2.5 ampere. Okay, this is ID. Now from this, can we find ID RMS, right, ID RMS, so we can write it as RMS value of ID. So ID RMS is equal to, ID RMS is equal to 1 by T integration from dt to beta t, dt to beta t, yes, it is a ID square into dt to the power 1 by 2. So is equal to, yes, we can write it as 1 by t, or I am taking this 2 outside, so it is like 1 by root t, right, 1 by root t into, yes, integration from dt to beta t. What is ID? It is a 2.5. So it is a 2.5 square into dt to the power 1 by 2, right, to the power 1. Further we can write it as is equal to, yes, is equal to, it is like 2.5 divided by root t, okay, into, yes, t, and after putting the limit, let us consider it as a t first, dt to beta t to the power 1 by 2. This can be written as 2.5 divided by root t, okay, into, yes, it is like under root beta minus d into t. So this root t, this root t, it will get cancelled. Okay, so it is equal to ID RMS. Therefore ID RMS is equal to, we can write it as 2.5 into under root beta minus d. What is beta? Beta is 0.833, 0.833, minus what is d? D is 0.5. Okay, so d is given, it is a 0.5, beta is 0.833. So if you check, it is equal to under root 0.833 minus 0.5. So it is a 0.577 into 2.5. Yes, it is 1.44, 1.44 ampere. This is the ID RMS we are having. That is the RMS value of the diode current, right? It is equal to 1.44 ampere. Are you getting the point? Okay. So this is about the numerical number 3. Numerical number 3 related to the boost converter. But this example is related to the discontinuous conduction. Okay. How to check whether the conduction is continuous or discontinuous? Yes, please check. First of all, we need to check for the continuous conduction whether with a given duty cycle and given input voltage, right? Whatever the output voltage specified is correct or not. Okay, if it is not, then we need to go for the discontinuous conduction. Okay, so in the next video we are going to discuss about the buck boost converter. Thank you.